This is a recording on, I'm going to give you a list of parent functions that you will need to know. So going forward from here, we just talked about analyzing functions, and we're getting an idea of what we want to do is get an idea of the potential functions that we're going to be talking about this quarter. And so, and basically what I've done is, what we're going to do is break them into some family of functions. So I'm going to give you the parent function of each of the families. And a lot of these are, some of these are you're already familiar with, and some will probably be less familiar. So, as we go forward from here, you're going to want to really get the basic, we'll get the 9 equations that I'm going to give you in your head, and also at the same time know the basic sketch of their graph. So you want to be practicing these, and I'm also just opened up a discussion that's worth points in Canvas that you'll be discussing these parent functions. So you want to check that out if you haven't already after watching this video. Okay, so here we go. The functions are, and there's 9 of them. I think I said that already, but the first one is one that you should be very familiar with, is y equals x. That's just a basic linear equation. And the graph of that looks like this. So I'll use a different color for the actual graph. It's a linear equation with y-intercept of 0 and slope of 1. And so it looks like that. The key here would be, and so when I'm looking to, when we're talking about these, when we're sketching them, you don't have to plot points necessarily and be that careful, but you do want to make sure you're not giving any false ideas. So it would be very important to go through the point 0, 0, and it should be a fairly straight line. Some of us have trouble drawing straight lines. You can see mine's a little bit wavy, but and it should be pretty much halfway between the 2 axes. Again, I'm not going to measure on your ability to do art, but I will look for, if the line is grossly curving, that would be something that you might get marked down for. If the graph is, or if the line is very flat, that would be a problem. So anyway, think about those sort of things. Okay, so that's the first one. The second one is y equals x squared, and I say second. They're not necessarily in any particular order. That's just the way I'm doing them. I'm actually just kind of doing them as they come to my head. They're not in any kind of a specific purposeful order. Okay, and then we'll again do this shape in red. So this is a parabola. A lot of you are familiar with parabolas. So it looks something like this. The key here is that it is rounded. Should be rounded, and it should be the vertex should be at the origin, and these arrows at the top should be going forever up and forever outward. There shouldn't be any curving back in towards the y-axis. And notice that 1, 1, I missed it by a little bit, but it should have gone through the point 1, 1, if that's a kind of a reference point for you. Okay, so that's the second one. Next one that I thought of is absolute value of x, y equals absolute value of x. And that graph is basically like y equals x, but the absolute value makes it rebound when it hits the x-axis. So it'll look like y equals x on this side, but then it rebounds off of the x-axis and looks like that on the other side. So it's a big V. Okay. Again, the key there is these should be straight lines, and vertex should be at 0, 0. Okay, next one is y equals the square root of x. This should look like the half of a sideways parabola, because that's actually what it is. So again, it goes to 0, 0. But this is going to, oops, oh no, I was trying to start to look too straight. Again, this should be curvy, so there should be a curve to it. It looks something like that. starts at 0, 0. I mean, the endpoint of that is at 0, 0. Does go through 1, 1. But like I said, it looks like a half of a sideways parabola. Okay, moving on. Here we go. Let's go back to here. Then we have y equals x cubed. That's a fun one. I affectionately refer to this as the mountain climbing function, because it looks like the path of someone climbing a mountain, because you're climbing up this really steep mountain, and then you come to this nice point where you can rest for a moment, and then you continue your climb on up. Isn't that cute? Note that one of the key points here is what's happening at 0, 0 is there's a flat point of just one point. It's flat, and the rest of the time you're going up. Also, these arrows should be going forever up and forever out, although the up, of course, is much more pronounced than the out. But there shouldn't be any curving back in. Oops, I did that in green. Sorry about that. That's going to be confusing because I did all the other ones in red. So I will fix that. Okay. Once again, it looks something like that. Okay, so that's y equals x cubed, and then the next one is the inverse of that. Y equals the cube root of x. So this one, just like the square root of x looked like a sideways parabola, this is going to look like a sideways cubic. So it's going to come in like this, real curvy like, and go like that. And again, that point at 0, 0 is actually a vertical point. It's one point that's vertical. So it's a line that's 1 point long that's vertical. And then also make sure this curves, and it does not curve back towards the x-axis, but it goes forever up and forever out. And here the out is emphasized more than the up. Okay, let's see, we got what? 1, 2, 3, 4, 5, 6. So we have 3 more. Now we're getting into the ones that maybe are less familiar. Some of those that I've done maybe weren't so familiar with you. So the next one is y equals 1 over x. And his close friend or cousin is y equals 1 over x squared. So these are fun functions because they have some discontinuities in them, or some breaks in the graph, so that makes them a little bit more interesting. And as you know, if you plug in 0 for x, that would make this undefined at 0. And we've been talking about that some for domains. So the domain of this function would be from negative infinity to 0, not including 0, and then from 0 to infinity, or all real numbers except for x equals 0. And the way this looks is you have what is called a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. And so this thing is getting closer and closer. And so the key here is to make sure that you show that on the y, it's getting closer and closer to the y-axis. There shouldn't be any parallel. You shouldn't draw anything parallel to the axes, because you want to draw it enough that you get the idea of what it's doing without drawing it too long, because if you go too long, it's going to start looking like it's parallel. And this guy over here is very similar, except for because of the x squared, it cannot produce negative y values. So similar type of curves, but they're both above the x-axis. So that's y equals 1 over x and y equals 1 over x squared. And then finally, the last one, and again, not necessarily for any reason why this should be last, we're going to talk about the ceiling function. The ceiling function is kind of a strange function that it may be very well that you've never even heard of this before. This is kind of the grand the parent of all step functions, because when you graph them, they look like steps. So the way this function works is it rounds every input you put in, it rounds it up to the closest integer. So if I plug in 0, of course that's an integer, so it stays at 0. If I plug in 1, or 0.1 though, that'll round it up to 1. So what happens is we get a little open circle here, and then it goes, there's a straight line right here. And it's closed there. Which means if we went backwards, there'd be a straight line here with an open circle. And so then when you get to 2, I'm sorry, when you get to 1, it's still at 1. But if you get a little bit above 1, it rounds it up to 2. So that means we have a little open circle there, and it goes like that. Open circle. I'm having trouble hitting those spots. Sorry about that. It should be right at, so at the point 2 to 3, there should be an open circle and then a line. Okay? So you can see why this is called the step function, hopefully, because it looks like a series of steps. So again, notice here the key would be that these open circle dots and the closed ends of the endpoint should be directly over each other. There shouldn't be any gaps in this. So when you plug in 0, it stays at 0. When you plug in 0.1, it hops up to 1. When you plug in 0.2, it gives you 1. When you plug in 0.99, it gives you 1. When you plug in 1, it gives you 1. But when you plug in 1.01, it hops up to 2. So that's the step function. So again, these are functions that you should get to know and be able to connect the equation to the basic sketch of the graph, because we're going to use these in the coming days ahead to graph and or to draw graphs of other equations based on transformations of these. We're also going to use them to gain some general knowledge so we can talk about all the functions in their family, because these two functions, the 1 over x and 1 over x squared, give us some real good clean indicators of what happens in any kind of a rational function, and the x cubed and x squared functions help us to understand what happens with polynomials and etc. So all these different these give us, so we can make some general notes about these 9 functions that'll help us understand other functions.